YouTube. In this video, we're going to look at a radioactive decay problem, which is a common type of thing to consider when we apply exponential growth and decay models. So we are also exhibiting what a decay model would look like over time. So let's go ahead and read through the situation. We'll present how this is a decay model and how we're going to interpret some of the things that are shared here. So we say in living organic material, the ratio of the number of radioactive carbon isotopes, we call these carbon-14, to the number of non-radioactive carbon isotopes, which is carbon-12, is about 1 to every 10 to the 12th of those. So basically we say for every one carbon-14, we have 10 to the 12th of these carbon-12s, which is really little to a whole lot. Okay, the thing to notice here is, or at least that we've observed, is that when organic material dies, the carbon-12 content, so this 10 to the 12th number, it stays fixed, whereas the radioactive carbon-14, it starts to decay, and I'm going to use a really common phrase here, but we're going to say with a half-life of about 5,700 years. So I'll come back to this statement right here, but basically what I'm telling you is this ratio right here, this number is going to decay over time, and it has a half-life. Okay, so when we talk about half-lives, at least with things decaying radioactively, we say over time. A half-life, considering the fact maybe it starts at some initial amount here, we have a decay model that comes through like this. Not a very good graph here, but we say an initial amount, capital A, we say, well, half of this amount would be this A halves right here. But essentially, we could say A halves, this is at a height of A halves at about right here. So when we talk about a half-life, we're saying it is this amount of time that needs to pass here. Let me switch out my colors here. We say it's this amount of time right here, 5,700 years, had to pass for this initial amount to be cut in half from its initial amount. And so we could say, well, you know, if we were to cut this in half, I'd have to go another 5,700 years. So if I went another 5,700 years, a better point would have been right here. We said, you know, it's doing this, okay, over time, and forgetting this part. So when we talk about a half-life, it is the amount of time that needs to pass for this to be initial amount to be cut in half, the initial amount of something. In this case, the initial amount is a ratio of something. So it says to estimate the age of dead organic material, scientists use the following formula, which denotes the ratio of carbon-14 to the ratio of carbon-12 present at any time t in t years. Really quick note, we say t equals 0. We usually allow to represent the initial amount. So one good thing to do is like plug in 0 and see what you get for an initial amount and prove that you get this amount out front. Let's take a look at this model. This truly is a decay model. They use this model right here where R is the ratio of carbon-14 carbon-12 present at any time, and T is years. So usually when we talk about a model here, we're saying that this is like our Y, our output, and this is our input right here. And so we can totally put this into a calculator. But lucky us, we've been given the model. But I do want to see this. This is actually a decay model. Decay models, recall, that are any model of this form, Y equals AE to the negative BX, where we put a stipulation on B. We say B is positive. Okay, so B, recall, is our rate, and we say that Y is like our amount that we have at any time, and we say that this A here is our initial amount. But this is truly a decay model because you can see that over here we say that we have a Y value. We say our initial amount was this ratio of things right here. We say e to the power of, now this negative t over 8223, we could rewrite this model as, and I'm going to do that. We're going to say y equals initial amount, 1 over 10 to the 12th. I'll keep that the same. E to the power of, and I'm going to write this as negative 1 over 8223. And this is times t, which would be the same thing as what we have up here right now, but you could clearly see that this is our b value, okay? Or at least we could say this negative. We should probably put it out front. We say this is the b value, 1 over 8223, and the negative is out front that causes this to be decay. Well, I'll tell you what, just like so many word problems, we've been given an initial value, or not an initial value, but at least some information initially, and we can actually substitute that in and go find what we want to know. So in this case, we say r, which is 1 over 10 to the 13th, is equal to 1 over 10 to the 12th, that we're taking this times e to the negative, we say negative t over 8223. Okay, so what we want to do is we want to solve for this t value, of course. So what we are going to do is this. We're going to divide. I'm going to write it this way. Divide both sides by 1 over 10 to the 12th. And I'll write it this way on the right side, not on the left. Because really when you divide with fractions, recall that we're just going to multiply by the reciprocal here. And so I'd say that, hey, 12 of these 10s up here cancel out with 12 of those 10s down there and leave 1 behind. So here we have, now arriving at this, we say a 10th is equal to e to the negative t over 8223. Now that we've isolated the base, which is what you normally do when you solve an exponential thing, we are going to rewrite this as a logarithmic expression where we have log base, well, our base is e. I typically write ln for this. We say, but log base e, e turned into 1/10. So we say 1/10, and we took it to the power of what? Well, we must have been taking it to this power right here. So we say negative t over 8223. So now I'm going to multiply both sides by 8223, And to get rid of 2 steps in one, I'm going to multiply by a negative 82.23. So negative 82.23. This thing right here is equal to a positive t. So I'm going to clean this up a little bit here. We say t equals negative 82.23. I'm going to write ln of a tenth. And we're just going to pull out our calculator and then look at this graphically. But we say in the calculator here, I'll do a tenth first. Of course, a tenth is 0.10, but we'll type it in that way. We say the ln of this times negative. So 8223, I'm going to call this negative. And we get about 18,934.15. So 18,934.15, and this is in years. So essentially, we could date something as being almost 19,000 years old if we knew that this was the ratio of a radioactive to non-radioactive. And you know, to look at the graph of this, I did actually go ahead and graph this, make it convenient for us. You'll notice that I put in for r of x the right side of our equation here. This was our initial model. Let me flip back over to here. This was our initial model right here. And what I did was I substituted, recall, I substituted this value in for r right here, which would be the left side of our equation. So when I go back over to the internet, you can see that what I was doing is I was graphing both sides of the equation. I say f of x equals this y value right here. And you can see this, I'm using very small y values. This is the ratio of material here. And then on the x-axis, way out here in time, a long time, because we have like, 5,700 year half-lives. So we say, all right, well, this 1/13 here, where do these two graphs intersect? And you can see that they intersect at 18,934 when they're both at that height. So interpreting this graphically, we could just graph both sides of the equation and see where they intersect at. Cheers.